The second type of partial fraction decomposition that we can do is when we have factors that are repeated in the denominator of the fraction. And these could be linear factors, these could be nonlinear factors. But sometimes you have a factor that shows up more than once. And we need to be able to utilize different techniques in order to solve for those fractions if that happens. So if we look at this example, we want to find the partial fraction decomposition for 12x plus 13 over x minus 1 and x plus 4 being squared. So the first thing that I would notice is that that x plus 4 is showing up twice. So when I break this up, I'm going to have to write a couple different fractions. I can't just write two different fractions. I'm going to have to write three. So I can say that I've got 12x plus 13 divided by the original denominator, x minus 1, multiplied by x plus 4 being squared equals the first fraction. I'm going to write a over x minus 1, because that's our first factor. Second, I'm going to have a b over x plus 4 without an exponent. And then third, I've got c over x plus 4 being raised to the second. And the reason I need to do this is I need to account for any power of that x plus 4. We could have had a fraction that only had one x plus 4, then found a common denominator, it ended up with both of them. Or we could have just had a fraction that had the x plus 4 squared. We don't know that, so we're going to account for any possibility as we're trying to solve for these fractions. Now, just like with any other partial fraction decomposition, I'm going to take this entire fraction and multiply by the original denominator, the x minus 1 and the x plus 4 being squared. So when I do that, this is going to help clear out all the fractions, and then we can start to group together common terms. So if I multiply those by the fraction on the left side of the equal sign, it's going to cancel out the entire fraction. And I just have a 12x plus 13 left over. If I multiply these by the fraction with the x minus 1 is going to go away, but I still have the x plus 4 being squared that will end up multiplying by the a. The b, one of those x plus 4s is going to divide out, but then I still have an x minus 1, and I still have one of the x plus 4s. And then for the c, the x plus 4 squared is going to divide out, but the x minus 1 is not, so I need to make sure to multiply that by the c. So now I've got a lot of multiplying out to do. So if I move this up, I've got this piece to start with would actually be an x squared plus 8x plus 16. This piece here would be x squared plus 3x and minus 4. And I do that just so I can multiply the a and the b by everything within those terms. So then I've got 12x plus 13 equals ax squared plus 8ax plus 16a, and then plus a bx squared plus 3bx minus 4b, and then finally plus cx minus c. So now I want to group these together. And notice I've got some x squared terms on the right side. I don't have any x squared terms on the left side. So I'm going to put in a 0x squared over here just to show me that that x squared needs to be some combination of the ax squared and the bx squared. Similarly, I can say that my 12x is going to be a combination of the 8ax, the 3bx, and the cx. And then my 13 here better be a combination of the 16a, the negative 4b, and the negative c. So I'm going to write a system of equation that will help me to pull all of these together. So for the x squared terms, the ones in black, I had a coefficient of a that needed to add to a coefficient of b, and that needs to equal the coefficient of 0 for the x squareds. I've got the x terms. I had an 8a added to 3 more b's and added to 1c should equal 12. And then the constant terms, we had 16 a's, and I was adding that, or subtracting, excuse me, by 4b minus c is going to equal the 13. So now our goal is to solve for a, b, and c so that I know what those original fractions were. Looking at this, I'd say the easiest thing to start out with would be to add the two bottom equations together. So if I take these and add those together, that's going to give me a new equation. 8 plus 16 is 24a's. 3b minus 4b is going to give me a negative b. And then c minus c is 0, and then add the right side, I end up getting 25. And then I'm just going to bring this top equation over, and I had an a plus a b is equal to 0. So then if I combine these together, since I've got common b values, just opposite signs, those are going to cancel out, and I end up with 25a is equal to 25. And divide off the 25, I get a equals 1. So then I know what a is. I can substitute those back in to get b and c. So a plus b equals 0 would mean that our b value is negative 1, because 1 plus negative 1 would give us 0. And I'm going to choose, let's say, the second equation to plug back in to get our c value. So that's going to give us 8 times 1 plus 3 times a negative 1 plus c is equal to 12. So I get 8 minus 3 plus c is equal to 12, which is really a 5 plus c is equal to 12. Which means that our c value equals 7 if I subtract off the 5. So these three values here, a equals 1, b equals negative 1, and c equals 7, become the values that we're going to use when we plug this back into our original fraction. So 1, negative 1, and 7. If I come back up here, that a, b, and c is what I'm looking at. So a over x minus 1, that means I've got a 1 over x minus 1 plus b, which was negative 1, over the x plus 4. And then I had c, which was 7, over x plus 4 being raised to the second power. This is our partial fraction decomposition of the original fraction that we had up here with the 12x plus 13 as the original numerator.